Today I want to discuss and continue our discussion on differentiability and what it means to be differentiable and some problems that we're going to see with being differentiable. So for a function to be differentiable at a point, it must be continuous. So remember, to be continuous, it has to have three rules that are true. The value has to exist, the limit has to exist, and the value has to equal the limit. And the slope of the tangent lines must be the same at the given point. So the slope from the left and the right side of that point, or that x value, they have to be the same as well. So when we talk about differentiability and we talk about continuity, we're going to see and we're going to examine all of those different parts. So example 1 is asking us, is the function continuous and differentiable at x equals 0? So to start, we look at, I guess this should be x equals 1. Sorry about that. X equals 1. So if we're looking at about x equals 1, the first thing we're going to do is talk and determine if it is continuous or not. So the first rule of continuity, does f of 1 exist? As I look into my piecewise function here, I have a less than 1 and I have a greater than 1. Since I don't have any equal to, I know that f of 1 is undefined. And there, with our first rule of continuity, we know that this function is not continuous. So we say that this is discontinuous at x equals 1 because rule 1 fails. Rule 1 fails. And we know that since it is not continuous, it's discontinuous, we know it's also not differentiable. Remember, for a function to be differentiable, it must be continuous. So we can also say it is not differentiable at x equals 1 because the function, and we can even say the function f of x, is not continuous. And that would be a nice answer if it was an extended response question. As we get into example 2 and 3, these are kind of my favorite. Some of you think that they're kind of like a puzzle, and I think that as well. So we're looking for values. They can be a, it can be b, k, in this case, example 2, whatever variable we want, but we want to make it differentiable for all values. So what does that mean? Well, again, it has to be continuous. So I guess we got to make it a less than or equal to. I'm making all kind of mistakes today. I see one down here too. Make that a 1. Anyway, so we want to be continuous. So we want f of 0 to exist. So when I plug in 0, it's got to make sense. So if I plug in 0, I get 0 squared minus k. And here, when I plug in 0, I get 0 to the third plus k. As I look through there, 0 squared minus k equals 0 to the third plus k, I know that negative k has to equal k. So this is talking about our limits, if you didn't realize that already. So I know that negative k has to equal k. I can add my k over. 0 equals a 2k, so k must equal 0. Then if I go ahead and look to make it differentiable, I've got it continuous. Now I've got to make it differentiable as well. So I know that 2x, my derivative on the left side, has to equal the derivative on the right side, which is 3x squared when I plug in 0. So we get 2 times 0 equals 3 times 0. And here we have 0 equals 0, so that's true. So when we know that if k is 0, then this function is going to be 1 continuous, and also the slopes are going to equal each other, and it's going to be differentiable as well. Example 3, we're going to get a little more complicated. Here we're looking for a and b values such that f of x is differentiable at x equals 1. So as I plug in my 1, again to make it continuous, I know that a plus 10, paper's kind of moving on me, is going to equal, when I plug in my 1 for my bottom piece, I have 1 plus 6 plus b. So I know that a plus 10 is going to equal 7 plus b. At this point, we just have a equation, two variables, so we have a minus b equals maybe negative 3. And a lot of times they ask for a relationship between a and b, so that would be our relationship. Some number minus another number has to equal -3. The AP, it definitely likes to do that kind of thing where you have to plug in numbers to make it a continuous function. But anyway, derivative. If I take derivative of ax squared plus 10, I end up with a 2ax. And we know that that's going to equal, when we take the derivative of the bottom one, which is going to be 2x plus 6. When I plug in my one value, I get 2a is going to equal 2 plus 6. So 2a equals 8, or a equals 4. Since we know that a equals 4, that's when this is going to be differentiable. I can also plug my 4 into my original, or my equation over here. I get 4 minus b equals -3, and I'm going to be able to solve for b. Subtract my 1, I'm going to run out of room. Negative b equals -7, so b is going to equal 7. And that's going to give us two values, a and b, so that this function is, one, continuous, but more importantly, it's going to be differentiable as well. And that will end what we're going to talk about with our differentiability and finding those values. Good luck!